we observe performance? That has to do with HPC workloads on HPC, large-scale HPC platforms. So we've done some work there. I'll tell you a little bit about that. Some final thoughts. There's a special prize at the end, so as long as you stay engaged with the talk, and we'll finish with some Q&As. So let's start with tau. And so this is what I began work on 33 plus years ago when I arrived at the University of Oregon. What our goal our objective was with tau was to try to create a framework for HPC performance problem solving, where we could think about a model that we use for observability. This is that model as shown in the upper right here, where we think about how we measure performance, how we capture information for an application that's executing on an HPC platform. And then, given that sort of model, we intend to implement technology that's associated with different levels of the architecture of tau, so to speak. That is composed of instrumentation. How do we expose events, information? How do we expose that to a tool, to a measurement system? That measurement system then is capturing information about those events that are taking place during the execution, captures that information, holds on to it during the execution, and then at the end produces performance data output. And then the third component here has to do with the analysis of that data. And there's a variety of ways that you can imagine over a 33-year effort that we've worked on this and done various sorts of things. Tau is an open source project. It's available for download. It's in broad use. I should say that one of the objectives is to have Tau be portable to every single HPC and parallel computing platform and programming language, right? And runtime system and any other types of parallel execution methodologies that you might think. We've recently produced a paper that gives you an update on Tau, looking towards the future. And throughout the talk, you will see there are some papers that are shown here that you can go off and look at later. These slides will be made available also, so you don't have to take notes. So what are our observability challenges? What are the challenges starting with Tau, going all the way back to its beginning? And we'll look at it from the point of view of instrumentation, measurement, and analysis and understanding. How do we get access to events? So we have an application that's in execution on an HPC system. How do we observe it? How do we see it? We have to have some way of having visibility into the execution. And so making those events accessible, there are really two approaches to do that. One would be a probe-based approach, where you actually use instrumentation within the application itself to make visible the events. Another would be a sampling-based approach, and these two things are distinguished from each other, and they're important both to implement. But that's the problem. How do we make events visible? How do we decide which events that we want to see? Because there could be events all over the place, in your application, within the runtime system, within the operating system. It could be events all over the place. And which ones are valuable to you? And so when you think about those variety of events, they may have different techniques for instrumentation and ways to get access to them and to expose them. Once we've been able to do that, then the problem is, what are we going to measure? What is it that we're interested in measuring and seeing? And that's where, because the measurement system is part of the application's execution. The application is executing, we're making measurements. So that becomes a real challenge. And one of the biggest challenges with respect to measurement is actually implementing the measurement system on the different types of platforms that we would want to run the application. And this could be a challenge because of the processors, the memory system, anything that you can imagine that where you would need to have something that works with that component of the system in order to be able to make measurements. There are different types of measurements. You can have profiling measurements, you can have tracing measurements, you can capture time information, you can capture other metrics. These are all observability challenges, and it's not just unique to Tau. It's true for any single type of tool that you might imagine. The big deal for us had to do with portability. It had to do with the ability to take these events, which might be abstract events. They might be abstract with respect to, I want to see that event, whether I'm running over here on this machine, or my laptop, or that machine, or something. I want to be able to see those same events. The measurement system itself could vary, could be different. How do I make it portable? And then finally, when we have a whole bunch of data, we can have a whole bunch of different types of data. What tools can we bring to bear to help to understand what that data looks like? In a nutshell, these are things that Tau supports. Tau is a very comprehensive and robust system. It supports a whole bunch of stuff. A lot of this stuff, some of this stuff is even historic, and it is even still supported in Tau. But there are things for instrumentation. We can work with different languages. We can work at different levels. The source, the compiler, binary instrumentation. We can support automatic instrumentation in some respects. We support all the variety of different types of measurements that you see for the different things that you see. We can do intranode, P threads, OpenMP, OpenACC, a whole variety of things. Internode, different types of communications libraries, different types of accelerators. All of this is supported in Tau, and we've built some analysis tools to help in terms of looking at profile data that can be very large scale, and also utilizing other ways to look at, you don't see it here, but tracing information. We can capture profiles and traces at the same time. We've developed some technology for a profile database where we could put some of this data. So all that's great, but whenever you're building a performance tool, you can't do it all yourself. So one of the real benefits, there's a variety of different ways in which we can benefit from what other people do. At the measurement layer, there's this technology for looking at processor performance counters. That's great. We utilize that. Other tools do too. But one of the very interesting things that we are taking advantage of, and other tools are as well, is profiling interfaces. And it's the idea that software developers, that are providing some technology, like API is a good example, right? They can build into their software a profiling interface that facilitates tools. This is the profiling interface for tools that facilitates tools' ability to use those software and to understand, see events within those software and to understand what they are. This has become very important in the heterogeneous applications and heterogeneous systems, because there's a whole variety of different components and software libraries, software interfaces that you want to see. You want to see the events associated and other information associated with those interfaces. So in addition to if you just look at the different profiling interfaces or P threads or OpenMP or OpenACC, CUDA, MPI, all of these things are providing interfaces. And what's the big benefit is that we don't have to instrument. We can use those interfaces with preloading of pre-instrumented libraries in order to see events and get access to those events. So an interesting example is the Cocos profiling interface. Cocos is a programming language that is trying to support performance portability through the ability to compile for and target different back-end executions. It has a profiling interface. Tau implements that interface, and it can capture certain events and to expose them to our measurement system. So here's an example, of looking at an application where we have multiple levels of instrumentation that are supported by profiling interfaces. All all the events here, you see it's probably hard to see, but all the events in this profile that we're capturing were generated through profiling interfaces. Tau is just implementing the interface and connecting it with our measurement system. It also points out the heterogeneity of this application. It uses NPI, it uses CUDA, it's using COCOS. COCOS underneath is doing a variety of different things. If I did not have that profiling interface, I wouldn't be able to see these events. And so it's very important. Once we're able to get access to the events, then we can capture the information in Tau. Here's another interesting example. This is an application when I was 2 or 3 years ago in Helsinki, working with the University of Helsinki. A group there is developing Glossiator. Now, interestingly, when they developed Glossiator, they built their own profiler. They built their own profiler. And so they had a profile interface called PhiProf. That was the name of it. Right? And they used it, and it was great. So when we looked at that, we said, that looks a lot like what Tau does. So why don't we just re-implement your interface in Tau, and then boom, you can get the whole measurement support system that Tau provides. And that's what we did. So we re-implemented PhiProf, their profiling library. What's important about this in an application is that if you have developed your own profiler interface, the events associated with what you develop that has meaning to you. It means something to you, and that's what you want to see. You've been using that, right, in your application, and that's what you want to see. Okay, so we have to honor that. We have to say that semantics is important for the application developer when they move from different platform to platform, because it gives them the semantics when they're thinking about their performance. So we re-implemented it. But in addition to those events, suddenly they got all these other events. They got OpenMP, they got MPI, they got a whole bunch of other stuff that they had not been able to get before because they just didn't have the talent to do that. That's not what they do. They develop the application, they don't develop tools. So, interfaces are important, I guess, is the message I want to try to get across. Now I'm going to switch to something a little bit different. Okay? Tau, the way that Tau works is that Tau will give you a profile for every single thread of execution. And we think about that with respect to what you might think of as a context graph. So an event occurs, and when the event occurs, we look at that event and we ask, what's your context? What thread are you running in for this event? That becomes the context. We think of it as the call tree, if you will, is the thread context for this event. Tau will collect a profile for every single thread of execution that ever has an event. And so every thread, in your program, Tau will collect the events that are in the context of that thread. That's one way to look at performance and to think about performance. I want to see what every thread is doing. Another way to look at performance is to see where the work is done. Not who does the work, but what work is done. And when we started to work with a group that was developing an asynchronous multitasking runtime system, it suddenly broke Tau. Tau broke because this type of runtime system, it generates many tasks. And these many tasks overwhelm, essentially, the execution. And it's a separation of how work is generated to do, and then the tasks that do the work. And that was a problem for us. So instead, we developed what we call the Autonomic Performance Environment for Exascale, or APEX. The distinction here is that APEX focuses on task dependencies. It focuses not on the calling context graph, but on a process level task measurement. And that became very significant when we looked at such AMT types of runtime environments that support multitasking. And there's many of them that do. Many heterogeneous parallel programming systems support task-based execution. As you can see some of them there. And so Apex was developed by Kevin Hupp, who was in our TAO group at Oregon. And the observability challenges that we're trying to overcome are exactly the same as TAO. It's not like we're getting away from having to look at events and that sort of thing. But now the perspective is on the runtime execution, asynchronous runtime execution. And so now we're, instead of looking at what is each little individual thread doing, we're asking about work management. How is this work being managed and executed? And what parallel resources are being assigned to do that work? And so when we look at that type of a system, an execution environment, we need to find information about things like which pieces of work, what type of work is taking the most time? Where's the critical path for tasks that are executing, right? How are the resources being managed? And just to give you an example, this is a large application that was developed using HPX, which is a AMT, which is a very sophisticated C++ based asynchronous multitask runtime system that can scale. And HPX is being run for this particular application. It uses Cocos as a programming part of the programming. But what you see here are measurements that are being made with respect to tasks, not individual threads, but tasks. And those tasks, you can see the dependencies between the task execution in this elaborated task tree, and here in something that is highlighting some of where the performance is taking place within those task dependencies. This is important because that's the perspective that we want. At the same time, you can also see what the resources are doing. In particular, that's showing you here what's happening on the GPU devices. Okay, here's another example. Turns out that Apex itself is not just limited to only these kind of unique AMT types of systems, but it can be applied in other contexts as well. And it produces very interesting information, especially in the form of traces, that help you identify where task behaviors are occurring, how resources are being used, and so forth. Let's look at something else that is kind of a consequence of thinking about profiling APIs again, profiling interfaces. If I wanted to instrument my application, okay, so I have an application. I want to use some tools. There's different tools out there. There's TAO. There's another tool called HPC Toolkit. There's Scholastica. There's a variety of different things out there, right? I want to use those tools. I want to use all those tools. Then I need to have instrumentation that allows me to connect to those measurement systems. So this is an idea that we started to bounce around of having an instrumentation library, right, that allowed you to stick in instrumentation into your program, right? But when it comes to which measurement system you want to use, then perf stubs becomes an interface that then can connect to the different backends that support the measurements that also are supporting perf stubs. It uses a callback type of interface, but it allows you, what does it allow you to do? It allows you to use perf stubs in different applications, where when you do so, you end up having a choice of what backend type of measurement platform that you might want to use. So we, for instance, are using that with TAO and Apex, but other tools are also using perf stubs. And you can do. The observability challenges with perf stubs is how do you make your instrumentation portable? How do you make it portable? How do you make it retargetable? How do you do this in such a way where if I don't want instrumentation that is turned on, I don't want it turned on, I want it in my application, but I just don't want to turn on, how can I do so that there's no overhead in making use of it? And how then do we implement this type of callback mechanism within perf stubs to enable this essentially retargeting or connecting to the different measurement systems? So perf stubs is interesting. From the initial perf stub implementation in the context of thinking about these types of task-based execution environments, it becomes interesting to think about something called task stubs. The idea with task stubs is that, let's say you're developing an asynchronous multitasking runtime system, just for fun, and I want to have a AMT-based measurement platform to use. Okay, so it seems like I might have my own problem of developing this type of technology, unless I could use somebody else's. Well, we have Apex. Maybe the thing that we could do is to develop another API called task stubs, where you can go into your application and insert for your tasking system events that will then translate to running a back-end measurement platforms like Apex in order to measure task performance. So this is just showing you, where you can go and find task stubs. It's an API for asynchronous task instrumentation that allows you to hook up the different back-end measurement technologies for that purpose. Zero sum, how are we doing? We're moving along. Zero sum. Now this is something even different. The idea is that, what's the idea? The idea is zero sum is that it's an observability problem, that we have an observability problem, but here, the way to think about this is that we want to understand an application in the context of an execution where some of the information that we want to get is actually at the system level. That's one way to think about it. So why do we care? Well, because if you look at Tau doesn't really do that. It is what is called an applications performance observability system. It gives you an applications perspective. Everything I see, those events I talked about, are application events. That's it. All the performance information is associated that I measure in Tau is associated with those events. So it's an application perspective. It's an application measurement, right? But there could be stuff happening over here in the system that I don't see because I don't have any way to see it. We built some stuff in Tau to let you see it, but it was kind of cumbersome and a little bit ad hoc. Zero sum takes a different approach. Zero sum says, okay, look, there's some interesting stuff when you start to run your application that we could look at and give you information about. In particular, information about what are your processes and threads doing, not necessarily event-driven, but just what are they doing, right? And what's the system doing? So the idea is that we want to have a tool that allows you to do user space monitoring of an application's execution, looking at its resources, looking at its processes, looking at other stuff that we could look at, right? And in particular, this might give you some clue as to why you might be having poor performance. Poor performance of your application running might be due not necessarily to your application, but how you configured it and how you ran it. If I don't give you a way to look at that, to give you some feedback as to the configuration and how it's running and so forth, you might think that the problem is an application problem, when in reality it's not. So the idea is that the monitor, zero sum is a monitor. It's a monitor, not like tau or apex. It's a monitor. It sits there and it monitors every periodically, like once every, I don't know, 1/10 of a second. There's a separate thread of execution for every process that will go and look at stuff and give you feedback. It will look at the application threads. It will look at the CPU hardware. It will look at GPU hardware. It will look at memory and so forth. And you can find out more about it in this paper. What are the observability challenges? Well, this is very different. Zero sum is very different from tau and apex that I've been talking about. How do I implement a monitor? You have your application. I'm going to say, I'm going to monitor. How do I implement that? Well, the way the zero sum works is that when you launch your application, it will get control. It will create another thread for every process. It sits there and runs periodically, once every 10th of a second or so. And we had to implement that. So that's a challenge. That's an observability challenge. How do you do that, right? For any type of application, we need to associate a performance view with a system behavior. What do we do? When we're monitoring and capturing this information, how do we make that association happen? We want to observe things that have to do with configuration, poor configuration, or things that are more like failure states or faulty behavior, and try to make sense out of it. Because the best that we can do that. And so the monitor aspect of this is what's unique. But there's other interesting stuff that the monitor can tell you. In particular, it can tell you something about how your processes and threads and everything are running on your platform. This gives you information about configuration and the use of the hardware resources. Where's the processes being placed? How are they using different NUMA domains on the compute nodes? Is there an oversubscribing on resources that's just going to be leading to poor performance and create imbalances? And part of what the information that we get is coming from job submission data, but it's also coming from things like /proc. /proc keeps a lot of information, but tau never looks at /proc. It looks at application events, right? We can and we have built something to allow you to look at /proc, but /proc is a very different type of data than your normal application events. So we can query /proc. We can get information about how the threads are executing the processes and the memory and so forth. We can find out, if there are other things that are going on as being told to us, by these systems level sources of information, that would allow us to better interpret whether we are getting good performance or not. So it's a application plus a system view will allow you to see that. We can sample metrics. Previously, if we wanted to do that in tau, we'd have to do something. We'd have to trace. We'd have to turn on tracing to get this. This is a monitor. You can just sit there and sample stuff, like for instance, GPU counters and GPU data. And we can see, different metrics and over time how those are changing. So this is just giving you some images to see that for a particular application, in this case, this XGC running on Frontier, there's 896 hardware threads that are executing, and I can see all that information and collapse it in different quartiles, so that you can see what the behavior is over time. It's not a trace. It's not a trace. It's a time-based sample, stream of samples on a per process basis. So, what is it good for? Well, let's look at an interesting case study. This is some work that's coming out of Oak Ridge National Labs. Iris is a framework that allows you to run an application on a platform that has multiple components to it that might be of different manufacturers and different types. And those applications run to use all those different components at the same time. So as you see here, for instance, if I'm using CPU in this platform, I might be using CPUs that are from AMD, Intel, or Qualcomm, or whatever. I have different hardware components, both processor, GPU, I'm possibly using different memory systems as well, and I want to run my application on this. The problem for the tools is that the measurement system now has to accommodate all these different interfaces and in places where it's making measurements. Well, that's what Iris does. What measurement system can we build? Instrumentation and measurement system can we build observability framework to work with Iris. So we worked with, this is a paper that is for my former PhD student who's now at Oak Ridge, that is looking at this problem and has used tools, our Apex tool in particular, to support this type of performance measurement in this type of heterogeneous environment. The challenge here is how you work with multi-vendor heterogeneous devices and runtimes. They have different runtimes, especially with respect to the GPUs. And how do you support multiple different types of measurements that you might make for those multiple vendors? And in particular, because this is a task-based execution environment, it would be nice to actually see some type of a runtime monitor to keep track of information as to how those tasks are being scheduled. And so we worked with Manil and his group in order to do this. This is showing an example of running a particular application with two different types of GPUs that have different types of performance information that you can capture with those GPUs. And we were able to use Apex as a way of tracking all this data within that Iris runtime environment. Okay, are you still with me? Now, in recent years, I've been very interested in problems that are kind of outside the traditional, what you might think of traditional applications, and in particular workflows, where if you look at high performance workflow systems, we're looking at something that looks like this. We are working with applications that are being expressed as these large task graphs. And the tasks that are executing, this shows you an example of one of those types of systems called an ensemble system. But there's other different types. There's scientific workflows, data analytic frameworks, many task ensembles. But the idea is somewhat the same. You have many things that are running together with each other, and they're interacting through some type of a workflow. Okay? These tasks that are running could be heterogeneous. They could be actually different programs, but those programs are interacting with each other as they're executing. But not all those tasks might be executing at a single time. Rather, some of them are executing, and some of them are using the resources that have been allocated from an HPC platform and are being dynamically managed with respect to those tasks that are executed. And you have questions like, how many resources do I assign to this task? What is the next task that's going to execute when those resources become free, and so on and so forth. This is very different from what we have been doing before, in the tools that we have been developing. And for me, what that indicated is that we have challenges for observability that has to do with how the workflow executes. What demands are it placing on the system platform, in particular, the dynamic resource management that's taking place when these tasks are executed. Tau and Apex, everything I've been talking about, thinks about the application as a single application, not multiple applications, but a single application. And so, I can get my hands around that application. But these are workflow applications that, oh, a whole bunch of tasks that are going on. What am I supposed to do? How do I think about performance of a workflow? Because before I'm only thinking about performance of this one application, okay? And so I need to think about how do I support measurements in a dynamic, sort of task-rich environment, right? And the types of things that I want to see are not necessarily the types of things I would look at with Tau or with Apex. I need to see things that have to do with resource management. I want to know, when a task is executing, or what resources is it executing, and when it stops executing, what happens? Because there's a runtime system that is managing all these tasks in execution. And for me at least, I realized that I have to think about dynamics here. I have to think about dynamic observation. And the only way I can do that is to implement a monitoring system. I need to have something that lets me look at events that are occurring during the execution and keeping information about those things that are happening. I need a monitoring system. I don't need instrumentation and measurement that is just baked into the application. I need to monitor. And so we started to develop a monitoring framework. The idea is that we want to support observability in application and execution environments that are dynamic, because the interesting things are the dynamic things. That's what we want to be able to see. And so we took an approach initially, was some work called SOMA, that was based upon a microservice implementation of this. How do you build a live monitoring system that is going to support not only making measurements dynamically, but sharing information? This is very different from what Tau does or Apex does. So we wanted to build a system where we could actually see distributed, scalable monitoring information during the execution, because that information becomes important in terms of the dynamic decision-making processes that the rest of that runtime environment might be supporting. So we built this out of a microservice called Mochi. We used something called conduit as a way to represent the data, because the data might not be the same. It might not be in the same binary format. So you need something to represent distributed data to reason about. And we integrated this with a very sophisticated ensemble computing environment called Radical Pilot. So that was fun, and these are two papers that might be interesting to read. But in the end, I didn't like it. So I said, look, it's got to be easier to do this. We have to be able to do this in a much easier way. In fact, I want more flexibility in how I implement a monitoring system. So we implemented Simon, a simple monitoring framework. And my wife and I used to have a cat named Simon, who now the icon for Simon. But we wanted to take a minimalist approach, something really basic, right? But that can support a lot of flexibility. And that's what we aimed for in the implementation of Simon. We had a paper at Heterogeneidade on this. And Simon looks like this. It's very minimal. The idea is that we have an application that's going to run on these nodes here. And what we're going to do is that we're going to create essentially observation points. And those will be in the form of these processes. A local process to an application node. It can tap into measurements that might be made, for instance, with Tau through an interface to Simon. And then Tau would periodically just publish that data. And the monitoring system then just consumes it. And then, this is real basic, but then allocate. The other thing that just annoyed me is the idea that, I can't look at performance information online, and if I wanted to look at it online, why not assign resources to the monitoring system? So we did that too. You can run your application and assign a whole node to Simon to do analysis of that data, dynamically on the fly. And so that becomes a part of the Simon system too. It's very simple. You might look at it and it looks pretty simple to me, right? And then we implemented it using some simple mechanism for doing that. We did this all within a matter of a couple of months. We used Python for our assignment processes. Why not? And Zero and Q, which is a messaging layer to implement the communications. And then we tried to apply it. And we found out that we could do so fairly easily. And this is an example of that same XGC program that I was showing you earlier that we were looking at with Apex, and as well as with zero sum, right? And now I can look at it with Simon. All Simon is the monitoring system, and it just, taking in whatever, performance information or any other information that it might get during the execution. And this is showing you those same familiar GPU metrics sampling slides that we had, and we ran this on Frontier. I'm not claiming that this is at all scalable or anything like this. I'm just saying that it was a way to add value of observability value to an environment workflow system, right, that I didn't have any other means before to do. Okay, final thoughts, and now I've actually lost something down here, but I'll wrap it up. Okay? I think that supercomputing throughout its history is fueled by heterogeneity. That is, the change, the flux that is taking place across a variety of architectures, hardware, software, everything. Right? And performance observability, the things that we're interested in, I'm interested in, is always trying to keep up with that. Right? And so we need to think about those challenges and how we resolve those challenges for the next generation of supercomputing systems. And it's getting more complex, right? Is that this heterogeneity is a lot more fast and rapid these days. You see, like in terms of the systems, the diversity of types of systems. In particular, there's even proprietary access to certain technologies that make it difficult to be able to build observability tools. And we want to continue to do this. So the question becomes, do we need to do something even more than we're doing? I believe that observability is critical, that you're not going to be able to run these types of platforms and applications without having some type of way of seeing what's going on within those systems. Right? And in our case, it's always been thinking in terms of high performance computing. Right? But now there are different use cases of HPC. HPC observability, I think, is important. Things like integrated applications monitoring is important. The ability to support auto-tuning in situ. Thinking even about observability as a language abstraction, so that I can ask questions about it during the execution from a language perspective. And even having hardware dedicated to observability. You might be asking yourself, what's that? Well, I actually lost the other text that showed you. I wrote a paper back in 1990 that had to do with making hardware dedicated for performance measurements, and that's what it was called, Hypermon. That's what it looked like. Okay. I want to thank you for hanging out to the end. I also want to acknowledge my colleagues, main colleagues, Samir Shindig and Kevin Tuck, who have worked with me for a very long time. Samir is also a part of the company Peritools. And because you hang out to the end, I told you there's a special surprise. And I'm sure all of you probably know, SC is one of the main conferences, right, in high performance computing, and it's been going on since 1988. I have been to every single one of them. I was a graduate student back in 1988, and I got to go to my very first one, and I've been going to SC ever since. So one year, we decided to make tau pins. That's what it looks like. And we made way too many tau pins, like 1,000 of them. And I've been giving out tau pins to people at talks ever since. So if you're a student, you get first dibs. I have 12 of them here. And actually, really only have 11 because I have to give you one. Okay. And but if you want one, you're welcome to it. So here's your.
Okay, thank you very much.
And that's it.
All right, Alan, thank you very much for the talk. Well, we have time for questions. Right? We don't want to rush and just want to take as much time as you can give us to answer questions. So please, if you have any question for Alan, you can make it in Portuguese if you're not feeling like in English. I will translate. Embora?
I can see why we need to see the distribution of the different software and running together, and why we need to optimize. Vou cantar
Estava muito bem.
Eu entendo por que a gente tem que fazer, a gente tem que observar e otimizar todo vamos dizer assim, cluster de software rodando junto, e sei que isso vai gerar uma otimização melhor do que os softwares individuais. Mas eu queria saber o ganho que a gente tem entre otimizar, vamos dizer assim, os recursos distribuídos ou fazer, vamos dizer assim, uma boa otimização individual de cada software. Se a gente realmente tem um ganho tão significativo assim.
Rodrigo. Thank you, Rodrigo. Very nice questions. I'll try to. So if I know you understand English, so if I make some twist in your question, just flag. So Rodrigo is interested to know what makes an observability of the whole workflow in a cluster of different applications. What is the gains you have of observing all the applications together compared to observing all these applications individually?
Right. Yeah, that's a good question. And the way to think about it really has to do with how they interact. And mainly when you're looking at this, the types of things you're concerned about are how the resource is being used, right? And so if I wanted to know, just try to keep it simple. So I have a set of resources and I'm running these tasks on those resources, and they're running in different, sort of on their own independently. Let's just say that they're independent. So how do I assign resources like nodes or CPUs or whatever to these tasks? That's a question. So let's say that I did that. Now I have these tasks running, right? And some of them are finishing, and some of them are continuing to run. Some of them, are using certain types of resources like GPUs maybe. Some of them are maybe running on multiple nodes, so like their API-based applications and so forth, right? How do I ask the question of what resources are being used now, right? I don't know that unless I'm able to communicate the information across those tasks to something that will look at that and say, oh, I see that, right? And now imagine that you have a whole bunch of tasks that are executing. I've got tasks I have tasks that are executing, and then I got a whole bunch of other ones that want to execute, but they're not right now because there's no resources, right? And interesting questions arise. Some task over here is executing, and then stops executing. It gives up its resources. now the scheduler of this task system, right, needs to make a decision. Who's going to run now among these set of tasks that are running? So I have to be able to run, and I need to be able to use a resource that is now free. How do I know how much of that resource to use? There's interesting questions that arise. The question, from a performance perspective, is not so much what the individual tasks are doing, but what the collective performance of those tasks, right? How well is the system being used? And I can't see that just by looking on an individual task basis. That's the problem. And it in fact is interesting even more than that. It might not really matter how well the task is running. It really only matters how well the collection of tasks are running. And that's what you see in these very large scale task systems, is that what they're trying to do is they're trying to manage the workload. They're trying to manage the workload on a set of resources, and that workload is dynamic, and it could be interacting. And you don't see those interactions, you don't see those dynamics unless you're looking at across the entire collective of tasks.
And during the execution.
During the execution.
During runtime.
That's right.
Also right.
That's right.
I think Rodrigo deserves a pay.
Yeah.
I think he deserves a pay. Right? Give you a
That's right.
Then we can simulate more questions. Thank you, Rodrigo.
I have 10 more minutes. 10 more questions.
More questions. Vitor. You have to speak up, otherwise, out here. We cannot hear you.
It's a very interesting problem, and frontier problem nowadays with a lot of computing demanding on the world and a lot of application and tasks and experiments. And my question is about the level of confiability of the monitoring systems, and if these monitoring systems are to monitor são também monitorados, no caso. Monitoring the monitor jobs. Because to me, tasks are executed, and these tasks that maybe have some errors or I don't know, stuff to debugging, etc. But the monitors have a lot of importance now, and for me, these tasks have to get a lot of confiability level, like 100% confiability.
You got it?
You can repeat it and add
And also,
a little bit more.
I'm not sure if I got it right, but we want to know about like the tasks that are monitoring the application. If you have to monitor the reliability, the confiability, reliability. If there is, perhaps it was trying to say is how reliable can you say that the measurement is? Can you talk a bit about reliability of measurements?
Yeah, well, yeah, this is actually a bit of a deep topic for me because it was one of the core things in my PhD thesis, and it has to do with this idea of uncertainty. Reliability or uncertainty is another way to think about it. So if I'm making a measurement, there's overhead. There's a cost to doing that because I'm running on the CPU. There's a cost. The question is that does it intrude? How does it intrude on the application's performance? I really sort of got down in the weeds, in the PhD work, because what I ended up doing was to try to figure out whether I could actually model the intrusion in such a way that I could actually take the measurement at the end and remove it to get a more reliable measurement. So I'll just tell you what I did because
Which is desirable to be very high. Right?
So here's the problem. I'll just tell you what the problem is, and then I'll come back to the reality. So what I ended up doing is I instrumented every single assembly language instruction. That's high overhead. Right? Super high overhead. And then I measured just the instrumentation and said, oh, okay. And this how much it costs. I divided it by the number of points that I measured. And then I ran it on this code, and I was able to back out the overhead. I call this perturbation analysis. So I developed some techniques for doing measurement perturbation analysis. And it worked, except it doesn't work. And where does it not work? It doesn't work in situations where you have non-deterministic execution. If you have deterministic execution, it works. If you don't, it doesn't work. And then that's when I stopped thinking, that's when I started writing my decisions. I said, that's a hard problem. Because the only way now that I could actually model that is to model every single thing about it, about the architecture, about the system. I have to model the entire thing. I'd basically have to simulate it in order to be able to solve the problem. Okay, now, fast forward, now, I don't instrument every single assembly language. That's stupid. I don't do that. I don't do that. So now what most tools would just tell you, they'll just tell you what the overhead is. They'll say, oh, we measured a 4% overhead. We had a slowdown of the total execution time of 5%. Then you go, oh, okay. And that's it. That's sort of it, what they tell you. Okay. Now, you still could very much have intrusion for sure. That's what that slowdown is. It's intrusion. It's intruding on the application's performance, right? But you don't necessarily know how. Now, you have to believe that there's other things that are going on, like using of a memory system to hold performance information or whatever it might be. Okay, now, so that's what we do. That's what everybody does, right? So we essentially don't worry about it, but you should worry about it. Now, there's a way I'm going on because there's more interesting things to say, is that, and that has to do, it essentially has to do with how you, in a dynamic execution environment, I'll just describe it that way. And what do I mean by that? In a monitoring system, I would not implement a monitoring system unless I wanted to actually look at the performance information during the execution. That's what the monitoring system can give you. It can give you a way to look at that information. All right. So if I want to look at the information, I have to implement the monitoring system, and so I have to come to some agreement that the monitoring system is not going to impact the performance negatively. Rather, the monitoring system there is to help me understand performance so that I can impact it positively. And that becomes an interesting question. It's an interesting question as to can I build a measurement system that is looking at performance information during the execution and making it accessible. I'm going to make that capability possible to make it accessible, right? And am I still going to feel good because now I'm really impacting it. How do I get distributed performance data to look at that? Think about load balance as an example. How do I know whether my application is load balanced? I don't know, because the load balance information is distributed. I have to query it to ask that question. So the question, do I feel okay, in having a monitoring system in place? So why would I feel better? Because now, if you look at HPC systems, like ones that are using GPUs, or in particular the ones that are using GPUs, applications, they're using GPUs, predominantly using GPUs, because that's where the performance is. They have this, they had this 64 thread CPU sitting over here doing nothing, just basically doing nothing, except, calling the CUDA routine. That's what it's doing, sending CUDA kernels over and over. Yeah? So those threads, what are they doing? Well, maybe you have to use one of those threads. So this question is whether the overhead intrudes and blah, 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 impacts the performance, blah, 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 But I have unused resources. So, I would like to think more along the lines of how do I think about the monitoring performance observability, I'll use that term, as a first-class part of the application. Yeah? And that in many applications, if you know, what do many of these applications do? That they create enough processes so that each process can talk directly to the GPU. That's what they do. So that's what they do. So a lot of time, there's 4 GPUs on this node. I'll create 4 API processes, each one of them talking to a GPU. I got a whole bunch of threads that are doing nothing, just nothing. So I could implement a monitoring system with very low impact and low overhead. I think I could do that. And I'd like to see more of that type of reasoning about this type of problem. You see what I'm getting at?
Okay, thank you.
That was a long one.
You deserve the P as well, right?
I deserve.
Any questions? More questions? Anyone wants another P? I have.
You already have.
I think I should deserve my P. So I will take a question. I would be, well, first I have to say that I see that there is a lot we can do to improve our tool by incorporating some of the stuff that we've done here. And thank God it's open source, so we can use it, stand in the shoulders of giants, and to go even further. So seeing you talking about this also help us to understand how that would fit together, right? So I definitely will chat with you after to discuss that. So thank you for that. I have 2 questions. One is related to the zero sum, where you implemented monitoring tool, right? How, I don't know if you've done that, but if not, do you have any idea how to do this? How can you connect what you're measuring with zero sum to the specific process or to the specific line of code that is doing work at that time, consuming that resource? Do you have means of doing that?
Yeah, so zero sum is the way that it's working is that it's not instrumenting, at a sort of a code level. That's not what zero sum does. But Tau and Apex do, and you can actually run Tau and or Apex with zero sum. You can do both at the same time. So that said, as an example, here's an example. So the question is, I showed you some things with zero sum where it's sitting there sampling. It's sampling. It's a monitor. It's sampling information. So it's sampling the GPU's statistics, metrics, and so forth. I could turn on GPU, CUDA profiling. I could have turned that on in my application to make profile measurements. And so I can see in Tau, where those calls are happening, to the CUDA interface.
And you can associate that with the monitor. Okay, that's great.
Yeah. So you see where those calls are taking place. So anyway, the point there, I think the comment there is that you can couple these two things together. A sort of the event-based, application code-based type of measurement, and then the sampler, which is looking at essentially things that are happening that it can get access to. It could sample CPU hardware counters. It can sample the GPU counters. It can sample /proc. It can do a whole bunch of other stuff.
Yeah.
But it's not.
Performance counters.
It's not instrumenting the code.
Performance counters. Like
That's what Tau does.
Okay, great. All right.
So, yes.
The other question is related to Apex and the workflow system that you like, Soma and Simon. So when you look at the workflow, you can also look at it as a bunch of tasks happening as big DAG of tasks, right?
Yeah.
Is it not like Apex work, like doing that, measuring independent tasks, how they are working? Could we use the same way of Apex to measure workflows?
Right. Yeah, that's a good. Yeah. So there's kind of a continuum when you think about task-based applications of how those tasks are actually implemented, and that continuum you can actually use the term workflow to talk about anything within that continuum in some sense, right? Yeah. But there are true sort of task-based. How to say it? It's not true. There are task-based systems that are very fine-grained, like even with respect to OpenMP. OpenMP supports tasks, right? So it's a task-based system. It acts like a task-based system. Of course, it acts like a whole bunch of other things too. But there are types of systems. StarPU is an example, right? Parsec is an example that are fine-grained tasking. They're fine-grained. HBX is an example of this. And so they're task-based, but they're very fine-grained. And so this continuum might go from that all the way up to something that is very large-grained, where you have tasks that are part of like a scientific workflow, for instance. That term is typically used to think about there are multiple scientific programs. One might be a simulation, one might be a visualization, one might be some type of a data management or whatever, and they're interacting at a much larger granularity, and I'm going to call that a workflow. Right? But there's others in between as well, and so your question is with respect to Apex, Apex tends to be more towards the fine grain. It tends to be more towards the type of task-based workflows that are kind of more fine-grained. And so it would not necessarily be, so let me also qualify it a little bit further to say in those types of fine-grained task-based types of systems, you really are thinking about a single application that just happens to be implemented using tasks. And so the code is more or less the same. And so I can instrument the code. I can instrument the code. I can also instrument the task interfaces and the tasking system. I can do all that. In these other types of workflows, the task may not be the same code. And that's probably a good way to think about the separation of something like Apex versus something where I'm using something else because that something else has to actually be running in a distributed way with respect to those tasks that happen to be more variety, heterogeneous types of processes. And so anyway, it's a good question because there is a continuum there, and it's a good question as to where I need to actually have the tool.
Okay. I made this question because I find that the way that you deal with task-based programming with Apex is very similar to the way you deal with different applications and different tasks from a workflow with Simon and so on. I found it a similar way of working.
I think,
But now I see it's a different levels.
yeah, that's.
Okay, thank you very much. Let's thank Alan again for this talk.
You need a pen.
Alan will be here until,
You guys need a pen, that's for
you're
sure.
gonna be here until Thursday next week, right?
Thank you.
Thursday, I'll be.
Yeah. You will be here until Thursday. So tomorrow and next week, Monday, Tuesday, and Wednesday, you'll be at room 26, 206 of DCA. So, se vocês quiserem conversar um pouco com a Alan, bate lá para poder trocar uma ideia, tá bom? Pessoal, muito obrigado pela presença virtual e pela presença presencial.
So that is if I survive my ayahuasca ceremony.
Oh yes, okay, of course. Anyways, thank you.
Okay, anybody want some more pens?
Pegar um pouquinho, por favor.
More?